Good day, everyone. Maybe it's morning, maybe it's evening, maybe it's the middle of the night. I don't know. But we are going to finish up chapter 9 and 10 today on bonding. I'll post in Google Classroom some things like your next quiz will be due this Friday. I'll have it set to be by the end of the day. So make sure before midnight Friday, you have finished the second chapter 9-10 quiz. So this is the second. This will finish up the material. And then next week you can expect to have a test, and it'll be a at-home test. And so you'll see what that looks like next week. But you should start reviewing, looking over chapter 8 material, 9, 10. So again, Monday I'll probably host a Google Hangout where when signed into your Google account, we could do some face-to-face, or at least just my face or my desktop, and you can ask all sorts of questions. And as always, you can send emails. You don't have to wait. You do not have to wait necessarily to. So yesterday we ended talking about polarity, saying that if you have a polar molecule, then it has an uneven distribution of electrons across across the molecule. And so today we'll get started by talking about some of their different properties. I mentioned this yesterday. If you put them in an electric field, we'll always find them weakly attractive to one another, where these partial positive and partial negative charges they are attracting. However, when you put them in an electrified field, they'll very strongly attract. And again, this is something that nonpolar molecules, they do not have to them. So when they're nonpolar, they don't have these attractive forces. So again, to talk about how to tell if it's polar or not, here I have these lovely molecules right here. And the first thing we said we need is a polar bond. And so here we have hydrogen bonded to sulfur. And sulfur is a more electronegative atom. And so with that, we could draw a dipole moment showing electron densities being pulled to this half of the atom. And there is also a dipole moment for that bond. And so overall, with these two polar bonds both pointing towards this direction, we say it has a partial negative side. That's upside down. That's okay. And over here, we have a partial positive. And so they're not the same as actual negative positive charges, but it's like a weaker version. But still, when you have opposite charges, they attract. So you have these polar molecules, there's going to be this attractive force that wants to pull them together. It's not nearly as strong as the bonds, but it's still going to be a force that pulls separate molecules together. Now, what you have to look out for, that's pretty pink, is some molecules will have polar bonds but be nonpolar. So take this carbon dioxide. So oxygen is pulling electron density to this side, and this other one is pulling electron density to that side. And so now you have electron density pulled to opposite ends. Well, that's not polar. So to be polar, it needs to have a negative side and a positive side. But this is negative, partial negative, positive in the middle. So this thing is, oh, that's upside down. Okay, let me go. Not non-polar. Oh, and that's backwards? Okay, I'm just not going to write. Yeah, there we go. So again, that was with so this is something you need to be thinking about with Vesper. So again, going back to this one. Again, the only reason it's polar is because it's bent. If this one were linear and they went in opposite directions like CO2, then it would also be nonpolar. But because this one happens to have non-bonding pairs, so again, they're not shown here, but these non-bonding pairs that are pushing these other atoms apart, because it's bent, that makes it nonpolar. So with that, things that are polar, or I said that's nonpolar, that's definitely polar, but things that are polar are going to behave a little bit differently than. So besides attracting to themselves, the effect that has is we're going to see very different boiling temperatures. We talked more about this your sophomore year, but polar molecules tend to have higher boiling points than non-polar ones. Again, because when you boil things, you're breaking these what are called intermolecular forces. So for example, if you look at the boiling temperature of water, it's 100 degrees Celsius, and that might not sound unusual because you've always known it was 100 degrees. But if you compare it to other things of a similar size, so consider H2S. Sulfur is right below it, below oxygen on the periodic table, and because it's less electronegative, the whole thing is less polar. So just by going down one element instead of 100 degrees Celsius, this stuff boils at -80. So you're going to naturally find it as a gas. Methane is completely nonpolar. So even though it's of a similar size, being nonpolar, not having any of these attractive forces, it doesn't boil or it boils at -180. So there's 280 degrees of difference, and it's all due to this concept of polarity. The other thing we can talk about is how well things mix. So we know like dissolves like. And so if it's polar, it's likely to interact with other things that are polar. And so this includes polar stuff with ionic compounds and polar stuff with other polar things. Water is commonly referred to as the universal solvent. So water can dissolve things like methanol and ethanol because they have these oxygen and hydrogens that make the molecules polar, or it could dissolve things like table salt or many other ionic compounds. And water is commonly called the universal solvent because there's such a huge number of things that it can dissolve. Now, if you want to dissolve something nonpolar, you need something nonpolar. That's why it's like dissolves like. So if you want to dissolve go away thing, carbon tetrachloride, you can dissolve it in benzene because both of them are nonpolar. Now, again, the easy answer to, hey, why don't oil and water mix? It's polarity. This is what we find. Many of you, if we were in the classroom, I would be holding up this right now. You could see, this bottles. Yep, I want to show you that there's a red side, but it always goes to the opposite. There we go. No, that's so close. Yep. Look at all that gross stuff. So you've seen this before. This is not new. Shake it up. Oh no, I hit the camera. Oh, what's going on? Okay, this is actually an even better view. I'll just take this thing off. So we have the stuff. Oh, that's fun. Sorry, this isn't part of the class, but the video of the video. Hold on. That's mesmerizing. Okay, we're back. Got it fixed up again. So yeah, oil and water don't mix. Short answer, polarity, because it's not necessarily that they repel each other. It has more to do with the fact that polar things attract each other and non-polar things just don't. And so they get kind of left out. So the last component of this chapter is looking at different types of bonding theories. So we've primarily only talked about Lewis theory, and in Lewis theory, the big idea is the octet rule. We know how many valence electrons each element has, so we know how many electrons it wants to gain to fill up its valence shell. But when you only go based on that, there's a number of different things it doesn't take into account, largely energetics, how resonance is a thing, how you can have things like expanded octets, and also why are certain bonds stronger or longer or shorter or weaker than others. And Lewis theory doesn't really address it, and it was the earliest bonding theory. So to build upon it, there is the valence bond theory. So with valence bond theory, we're going to be talking about hybrid atomic orbitals. Again, when you think of hybrid, you're probably thinking cars. Generally, if you have a hybrid car, it runs on both gasoline combustion and electricity. So it takes a little bit of both to work together. In a similar fashion, we're going to be talking about orbitals that hybridize, they mix together. So when we do this, we can take better accounts into some of the VSEPR structures and bond stabilities that we've mentioned. Then the last type we're just going to briefly touch on is molecular orbital theory. With this, instead of atomic orbitals, we'll talk about molecular orbitals hybridizing, but we'll get to that. And in this one, we'll better explain resonance, which, again, from the last video, resonance has to do with how certain structures have partial double bond character, where a single Lewis structure can't really show how they actually exist. So to get started, I want to point out a few things where Lewis theory breaks down. And for one, if we were to look at the ground state configuration of carbon, 2s2, 2p2 is the valence. If you were to look at these and say, hey, how many electrons could pair up to make a bond? You would say, well, there's only two. There's only two that are unpaired. These two are already paired up. However, when I had you do electron dot structures, I didn't have you do this one on the left. I said spread them out. So why did we spread them out? Which, again, earlier we would say this one would break the Aufbau principle if we were to go ahead and not fill up the 2s and spread them out. So why is it this and not that? So we know carbon makes 4 bonds with all single bonds. So what's going on here? So something else we could say is sometimes, not that the Aufbau principle tells us it wants to be in the lowest, but sometimes if they get energized, electrons could jump up, they can get promoted. And so maybe they are fully spread out, and this would have the configuration seen on the right. But if this was truly the case, if we remember what p orbitals look like, here they are over here, they form these figure 8 type shapes that are all perpendicular from one another. And when things are perpendicular, that would tell us that the bond angle should be 90 degrees. But from what we already know about tetrahedral carbon, are the bond angles 90 degrees? To that, we say no. We know that structurally, a tetrahedral is 109.5. So what's the deal? Why can it make this bonding? Why is it not 90 degrees? And how is it able to make 4 bonds? So for that, we look at what's called hybridization as a part of valence bond theory. And the idea is these are the atomic orbitals we've talked about, but that is how they exist by themselves. So if you have a single atom of carbon, then their orbitals do look like this. 1 spherical, 3 that have this figure 8 shape in different directions. However, when they want to bond with another atom, they have to do some shifting. So I've always thought of this as, again, you might have your room and you keep it just the way you like it, but if for whatever reason you all of a sudden have a roommate, you're going to have to move some stuff around. You might have to share a bathroom, a closet, and you're just going to have to make things look a little different to be able to accommodate someone else. So here's how carbon accommodates. It takes these 4 different orbitals and hybridizes them into what we call sp3 hybrid orbitals. So I want to point out that if you start with 4 atomic orbitals, you end with 4 hybrid orbitals. And these orbitals are degenerate. Now, we used this word a couple chapters ago, and what it means is that every one of these is exactly the same in terms of energy. So normally we would say this s is lower in energy than the p orbitals, but here all 4 of them are exactly the same. And so we'll also see that however many orbitals you start with, that's how many hybrid orbitals you will end up with. And so instead of having an s and 3p, go away, little thing, go away, go away, go away. I don't know how to make that go away. We have 4 degenerate sp3 orbitals. So also, do you notice how we named it? So each of these orbitals came from one s and three p orbitals, so it's conveniently called an sp3 orbital, and there's four of them. So now when we look at tetrahedral methane, carbon, there is four sp3 orbitals that are overlapping with the simple 1s of a hydrogen. So these hybrid orbitals could either overlap with other hybrid orbitals or just regular atomic orbitals. So hydrogen doesn't have to hybridize, so that's not a hybrid orbital. Something else I want to point out, that again, all of these bonds are exactly the same in terms of length and strength. So I mentioned they weren't 90 degrees, but even if they were, we would still expect an s orbital to form a shorter bond than the p overlapping bond, but they're all equal. So again, we know carbon hybridizes because it can make four bonds. All the bond angles are 109.5, not 90, and all of the bonds are equal in length and strength. So we can go ahead and look at some few other examples. So if we look at boron, it has 3 valence electrons, and we said it has an incomplete octet. Well, those 3 can spread out to form and then hybridize to form with an s and 2p orbitals. We get 3 sp2 hybrid orbitals. So there's 3 of them, and then for bf3, there's the fluorine can just donate a unhybridized p orbital. It doesn't have to hybridize, but again, there's 3 sp2 orbitals. So when you count s and 2p, that is 3. So 3 atomic orbitals, 3 hybrid orbitals, and with 3 hybrid orbitals, it can make up to 3 bonds. Beryllium is a metal, but it acts kind of weird. Here it can make covalent bonds. Again, we said it was linear. It has no lone pairs, so it only has 2 electrons in this 2s orbital. But in this case, it will promote an electron to spread out. So with a single s orbital and a single p orbital, can just ask yourself, hey, what would these hybrid orbitals be called? And it is a sp orbital. So we start with 2, we end with 2, and the name sp is because there's just one s and one p that make it up. So if there are 2 hybrid orbitals with an unpaired electron, then they're able to bond to continue finishing. So chlorine is able to form this overlap with its unhybridized 3p orbital with beryllium with 2 hybrid bonds. So 2 hybrid orbitals can make 2 bonds apiece. So really, I like getting to this part because we can finally explain how we have this expanded octet. Phosphorus pentabromide has 2, 4, 6, 8, 10 electrons associated to it, and that's breaking our octet rule. Well, we want to know, like, how is that possible? Now, previously we said you only get expanded octets when you're down in the third p block, 3p, 4p, 5p. So you're not going to find it in 2p. And the reason why is it's not till the third shell that you get d orbitals. So if you were to look at phosphorus, its first its valence looks like this: 2 that are paired, 3 that are unpaired, and there's this whole 3D that is just vacant. So they're there. Again, if we were in the second shell, this would not even exist. But the fact that it's there tells us that sometimes when it needs to, phosphorus can take an electron and just let it spread out. And now that you have 5 unpaired electrons in 5 different orbitals, then they can hybridize. And again, take a moment to guess, hey, what are these hybrid orbitals going to be called? There's 1s, there's 3 p orbitals, and there's 1d. And so it's called a sp3d orbital. So if we start with 5, we end with 5. So it's able to make 5 bonds. You could also have a non-bonding pair in one of these hybrid orbitals, but we're not going to focus on those. So we have phosphorus has 5 sp3d hybrid orbitals, each of them overlapping with a bromine, which would have just it's 4p, a half-filled 4p that it's able to overlap with. So again, it's only when you get to this third shell where you get these d orbitals that they can do this. So phosphorus, sulfur, chlorine, bromine, iodine, but you're not going to see this for nitrogen, oxygen, or fluorine because they don't have any d orbitals. They're not going to have expanded octets. And then here's a nice look at those 5 sp3d orbitals. There you go. There's that. Again, this table kind of summarizes these things. So if you want to know what type of hybrid orbital, you count up how many non-bonding pairs and bonding atoms are there. So for beryllium chloride, there's 2 things bonded to it, no non-bonding pairs, so it requires sp. BF3 has 3 things, so sp2. But here we have methane, we have ammonia, we have water. Even though there's 4, 3, 2 things bonded, water has 2 non-bonding pairs. Ammonia has 1 non-bonding pair. So there are still 4 total electron pairs. So just like when we did Vesper, we counted up how many different things we're pushing away from each other. And that same number is what determines here, in this case, it's sp3. Again, if there's 5 things bonded, sp3d. If there's 6 things bonded, sp3d2. And so just be aware that, again, you need the same number of hybrid orbitals to match how many atoms are bonding plus the number of lone pairs. Now, depending on what type of bond you have will dictate the rigidness, the flexibility of the bond. And so if we start with single bonds, here's ethane. Again, this is how we draw it on paper as a Lewis structure, but then here's how it looks when you start looking at these are all sp3 hybrid orbitals. Now with sp3, we have this overlap directly in the middle. Now it's kind of like a handshake. Look, they're both reaching out and you have this overlap in between. This is what is called a sigma bond. So electron density is shared directly between the 2 atoms. So right between. Again, it's a handshake or it's a nice warm hug, as Olaf would like. Now, because it's only a single interaction, ethane, and we could count up, has 7. 1, 2, 3, 4, 5, 6, 7. Because this interaction is directly in between, it still allows for a freedom of rotation whenever you have a single bond. So sigma bonds allow these to rotate. And significant about that is you might look at these two molecules that I have shown here. And if I were to ask you to draw 2 isomers, you might draw this one and assume that they're different. But in 3-dimensional space, they're actually. Here again, we have one of these wonderful models. So if you were here, we would normally have a lab where we play around with these model kits. And if you look at the bottom right here, again, this should be a good representation of, hey, look, I made the one on the left. But then if you were to look at the one on the right, it looks different, but really we can just flip this around and it's exactly the same thing. So with single bonds, with sigma, you have this freedom of rotation, and so they're not locked in place. So when we look in the 3-dimensional space, or on the 2-dimensional drawings, you can consider each one of these things on a carbon to be equivalent. So there's no set spot it has to be. It could be like this, or like this, or like this, but these are exactly the same thing. Now, if you have a double bond, this ends up changing. So again, a double bond means there's 2 pairs of electrons being shared, and the first pair is called, again, a sigma bond. So electrons are shared directly in the middle. But the second pair, this is where things change. This one's called a pi bond. And instead of being shared directly in between, you have electron density shared above and below the plane between the carbon. So again, this is a pi bond. Now, the biggest consequence of this, and here's a look at all of that on top of each other. So again, you see these are the bonds. It might look like there's three, but this is one sigma, and then here is one pi bond to make a double. Again, the Lewis structure representation doesn't really show that, but you just need to know that if there's a double bond, it's a one sigma and one pi. Again, the biggest consequence is it locks it in place. So again, here's ethane. With a single bond, it can rotate. But the moment there's a double bond, things can't rotate when there's a pi bond. And here's our model kit. So if you were to look at the one on the left, this is 1,2-cis fluoroethane. The one on the right, there is no rotation. With this double bond, you can't rotate it without it breaking. It actually takes a chemical reaction for these to be converted from one to another. It's called an isomerization, a cis-trans isomerization. So having a double bond, now these ones are two completely different structures. So you don't get the rotation when there's a double bond. Oh, and there's a video you should go and watch, but I'm not going to play it on this, but you can click the link in the separately posted notes. Now, if you have a triple bond, again, same story. There is a sigma, which goes directly in between the two atoms. There is a pi bond, electrons shared above and below the plane. And then there is a second pi bond. It's just pretty much perpendicular from the first set. So here with our triple bond, we have the first, and then here's one pi bond, and then here's a second pi bond. So that's a whole lot of electron density packed in between these two atoms. And again, there's no room for a quadruple bond to have another set. Again, when it comes to pi bonds, you again don't necessarily have rotation, though because it's linear, there's not really a point of axis to rotate anyway. So in your homework, you'll see some questions that look like this, just trying to assess how to spot a sigma versus pi bond. And so here we just have some organic chemical. Keep in mind, when you see CH3 or H3C, this is three separate hydrogen bonds. It's just the shorthand notation. And so even though you don't see the line for hydrogen here, just know that that's a separate hydrogen bonded to carbon, or in this case, here's two separate hydrogens that would be coming off. It's just the shorthand notation. But to say how many pi bonds, any single covalent bond only has sigma. So these are sigma, that's sigma, 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 sigma. But wherever there's a double bond, there is one pi bond along with the sigma. So here's one pi bond, here's a second pi bond, and where there's a triple bond, there's two pi bonds. So there's one pi, there's two. So to answer this question, it's simply there's four pi bonds. Again, if we were to ask how many sigma bonds, you just count up, well, for every bond, whether it's single, double, or triple, you'd still count it as just one sigma bond. Now, for the very, 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 very last thing in this chapter, we have molecular orbital theory. Now, molecular orbital theory is complicated. It's based off of wave theory, electron, and you have to model the electron, again, having those wave properties. And to do it justice, there's a good amount of math involved, and we're just not going to do the math. If you take some higher level chemistry classes in college, then you'll do the math there. But you essentially work out bonding and anti-bonding hybrid molecular orbitals. And the main difference between the hybridization we already talked about is instead of atoms hybridizing their own and then overlapping and sharing, here we're going to say the orbitals across the entire molecule hybridize. So it's not just carbon gets its stuff together and then overlaps with another carbon. It's they mix their own their own orbitals together. It's like it's like instead of having a roommate where one person has their side and your side, you just decide to go ahead and share the closet and mix all your clothes together and mix pretty much everything gets mixed. There's no distinction. So this gives better account for resonance. So to draw benzene, you could draw alternating double bonds either on the left or on the right, but we know that the bonds are actually equal, all six of them. So they're equal in strength and length, electron density. So it's like each one of them has one and a partial bond, partial double bond. And so this delocalization, it can be better accounted for whenever we say that, again, this resonance, if there's molecular orbitals. So then electrons can, instead of electrons being bound here or here or here, they're more able to circulate, which, again, experimentally, this one is more accurate, just it's a little bit harder to conceptualize. Now, the structure of benzene, just this is a fun fact. It was known for decades. Its molecular formula, C6H6, it was known for decades before anyone ever figured out its structure. And then at one point, Auguste Kekule, an organic chemist, he had a dream about it, not necessarily about benzene, but about a serpent eating its tail. And what had eluded the masses at the time was considering the possibility of a ring, a cyclic structure. And within a few years, they confirmed it was a ring, and now he's on a stamp. And there's a lot more to that story. In organic chemistry, you can learn about Kekule's rule, which tells you whether it's aromatic or not, but we're not going to talk about that. So with that, that's pretty much everything. So you should definitely watch this video. I might have shown you your sophomore year. It's a fun video. Hopefully you recognize some of the terms. But that's pretty much it. So again, definitely ask questions. I need you to turn your homework in on time. I need you to start taking quizzes on time. There's a handful of you that are going to get deductions on homework and quizzes because you're taking them and turning them in days later. And you got to, it's college, you got to stick with those deadlines. So anyway, have a fantastic, wonderful day. I hope things are going well. Keep yourself socially distanced and all that good stuff. So, okay, goodbye now.